Anyway, so far so good, we have linear phase, we are not doing badly. And if we look at the second filter in the Haar filter bank, we shall have something similar. So, let us look at the second filter, the second analysis filter. And that is of course 1 minus Z inverse into half. Let us again find out how this filter looks in the frequency domain. So, the frequency domain would show it as Z equal to e raised to power j omega, whereupon we have 1 minus e raised to power minus j omega by 2, and we play the same trick. We take e raised to power minus j omega by 2 common, and we have e raised to power j omega by 2 minus e raised to power minus j omega by 2. And once again one can recognize this is essentially 2 j times sin omega by 2. So, now I can simplify this, put it all together. Once again, I look at the magnitude response first. The magnitude response is the magnitude of this, and that is easily seen to be mod sin omega by 2. Let us sketch the magnitude response as a function of omega. Again, we will sketch it only between 0 and pi for the reasons that I have just explained. So, it will have an appearance something like this. This is going to be 1 here, this is mod sin omega by 2. Now, for the phase response. Now, please remember last time we had a convenient situation. We had two terms, one of them contributed no phase, the other one contributed a phase. So, we were comfortably put. This time we have to be a little careful. So, let us make life easy by first looking at only 0 to pi. Remember, we are going to have conjugate symmetry. So, let us consider omega from 0 to pi, and let us look at the frequency response expression j e raised to the power minus j omega by 2 times sin omega by 2. Sin omega by 2 is non-negative, so no phase contribution here. However, both of this term and this term have a phase contribution. In fact, the phase contribution is 90 degrees or pi by 2 from here and minus omega by 2 from here. So, overall the phase contribution or the phase response is, only between 0 and pi, pi by 2 minus omega by 2. This is contributing essentially j in the expression, and this part is coming from e raised to the power minus j omega by 2 in the expression. Let us sketch this response, I mean the phase response. So, of course, at omega equal to 0, it is going to be pi by 2. And at omega equal to pi, it is going to be 0. This is the situation. Now, once again we have linear phase. Well, almost not quite linear. If it were strictly linear phase, this would have been a straight line indeed, but a straight line passing through the origin. So, it is not really linear phase, this is called pseudo linear phase, seemingly linear phase. In fact, for completeness, let us draw the magnitude and the phase response all the way from minus pi to pi for both of these filters now, for the sake of completeness. So, the situation is for the filter half 1 plus Z inverse, the overall magnitude response should look like this, between minus pi and pi, I mean. Essentially mod cos omega by 2. And the phase. This starts at plus pi by 2 here and goes up to minus pi by 2 there. Passes through the origin, of course, a straight line. For the second filter, the overall magnitude response looks like this. Essentially a sine, mod sine omega by 2. And the phase response looks like this. Starts at pi by 2 there and goes to 0, it is a straight line segment. Here it would start, now that is interesting. You know, the phase on this side between minus pi and 0 needs to be the negative of the phase between 0 and pi. So, it will be a mirror image. These are lines, straight lines. So, we call this pseudo linear phase. Now, one point needs to be understood. There is a peculiar situation at the point omega equal to 0 here. The phase is both pi by 2 and minus pi by 2. How can this be possible? Well, the answer comes from the magnitude response. The magnitude response at that point omega equal to 0 is 0. When the magnitude response is 0 at a point, the phase response has no meaning. The phase response could be anything. You see, it means that sine wave at omega equal to 0 is anyway being destroyed. So, what consequence is the phase response? That is why there is an ambiguity in phase or a discontinuity in phase at the point omega equal to 0 in this phase response. A small detail, but important when we try to understand this filter bank completely. Anyway, coming back to these magnitude responses now. If we consider the two magnitude responses together, in fact, let us first consider the frequency responses together, both magnitude and phase. A very interesting property emerges. You see, suppose we add them. So, suppose you take, I do not even need to substitute z equal to e raised to the power j omega. Let me keep it as it is. So, half into 1 plus z inverse plus half into 1 minus z inverse. It is very easy to see this is equal to 1. A very interesting consequence. What does it physically mean? It physically means that if I were to send a sampled sine wave of frequency omega into one of these filters and then the other, and if I took these two sampled sine waves from the two filters and put them together by adding, you would get back the original sine wave. So, sine wave at frequency omega is split by these two filters in such a way that the parts can simply come together and reconstruct the sine wave as it is. Now, let us look at something more interesting. What can we say about the power? So, recall that if you give a sampled sine wave, a sampled sinusoid to a discrete time filter, let us say the angular frequency is omega and the frequency response here is h of omega. Then the power that emerges from here is proportional to mod h omega squared. So, in other words, whatever is the power of the sampled sinusoid with angular frequency equal to omega here is multiplied by mod h omega squared when it emerges at the output. So, the squared magnitude of a frequency response is indicative of the change in power of the sine wave when it goes through that discrete time filter. What can we say about the power change of a sine wave when it goes through either of these two filters here? Let us see. So, that means in other words we are asking the question, what is the magnitude squared response in the first one? It is mod cos omega by 2 the whole squared, and in the second one it is mod sin omega by 2 the whole squared. And lo and behold, when you add these you get 1 as well. That is a very, very interesting observation. Not only does it happen that when you add the two responses together, you literally took 1 plus Z inverse by 2 and 1 minus Z inverse by 2, the actual frequency response is irrespective of Z. In fact, I said there you did not even need to substitute Z equal to e raised to the power j omega. You just added the system functions together and you got 1. So, if you put a sine wave of frequency omega, I mean a sample sinusoid of frequency, angular frequency omega, and looked at the corresponding emerging sine wave on the top branch and the lower branch and just added them together, you would get back the original sine wave. Not only that, what we have just shown is that when you multiply, if you look at the power emerging from the upper branch and the power emerging from the lower branch, the powers also add. So, in fact, you have two kinds of complementarity in the filters. This is something very, very interesting here. So, if you call the frequency responses of the upper branch and lower branch respectively as H upper omega and H lower omega, upper branch, lower branch, then two properties are immediately satisfied. H upper omega plus H lower omega is equal to 1. This is called magnitude complementary property. And in addition, mod H upper omega squared plus mod H lower omega squared is identically equal to 1. This is called the power complementary property. A very, very interesting result. The Haar analysis filter bank is both magnitude complementary and power complementary. In fact, I leave it to you to study the synthesis filter bank and come to a similar conclusion. The filters are magnitude complementary and power complementary. Whatever it be, this is something striking. Now, you see what I mean when I said the filters have individual properties and collective properties. Magnitude complementarity and power complementarity are collective properties. The low pass and the high pass nature, if you recall, the second filter that we had was high pass, because it emphasized higher frequencies and de-emphasized lower frequencies. So, the low pass and high pass properties are individual properties. The magnitude and the power complementary properties are collective properties. So, we have filters with individual and collective properties forming two filter banks, the analysis filter bank and the synthesis filter bank. Now, the idea of a filter bank is very deeply entrenched in multi-resolution analysis. In subsequent lectures, we shall study this connection even further. So, for today, we shall conclude the lecture here by noting that we have already established even more deeply the frequency domain behavior of the filter bank that we brought out in the previous lecture. Thank you.